kind of filling in the gaps. I've noticed that as we kind of go through and talk about, different aspects of threat hunting and stuff like that, that it's not uncommon to run into, I don't want to call them basic subjects, they're not, but there's stuff that like some people may have picked up on years ago, and then there's some stuff that like, if you haven't been exposed to it, it's kind of hard to know how it works. So I want to, and that's part of what Fireside Fridays is all about, is filling in those great gaps. So I wanted to talk a little bit about routing and VLANs this week. Thanks to Herman and Emily, both of them in chat. Please give them a warm thank you for helping to develop this content. And I got a couple of hands-on things you can do. I'll kind of switch back and forth between Windows and Linux. So if you've got at least one of those, there'll be a couple of commands for you to play around with. So let's talk about routing. So we talked about layer two last week. We talked about switching. So if we move up our OSI model to layer three, this is where routing comes into play. So routing is based upon the addressing that's being used by whatever protocol is encapsulated inside of the frame information, right? So if we are on an Ethernet network, we got Ethernet frames. There'll be some layer three protocol encapsulated inside of it. The one we tend to use is IP, which means the information that's used for routing tends to be IP address information. Predominantly, what's used is the destination IP address, although it is possible to sometimes use the source IP address. I remember many moons ago, I developed a hack where you could, if you could get compromise somebody's border router that was based on Cisco, you could go in and do a little magic with policy-based routing such that any traffic trying to come into their network, you could route across the internet to where you are. You could route it through a system you control. You could sniff it, you could change it, you could do whatever you want, and then you could send it back and it would eventually make it to that network. And then as they tried to transmit out to the internet, policy-based routing would again send it down this GRE tunnel so that you could go through and sniff it and do whatever. And it would do that, only adding in one additional hop. So if somebody was looking at like the TTLs, they wouldn't be able to detect it. So if you could compromise their border router, you could actually sniff all of their traffic from a remote location out on the internet. And what allowed me to do that at all was policy-based routing. Thank you, Cisco. That made it so much easier to compromise their customers. So so yes, sometimes source IP can be used as part of making routing decisions. Predominantly, what most of us use for routing is static. We go in and we kind of manually assign what we want to use. But as networks get larger, you really need to be using something dynamic, and we'll talk about some of the possibilities around that as well. So a couple of little hands-on walkthroughs just so we can kind of look at some routing tables here. Let me pull up a system that might have an interesting routing table on it. Oh, well, that's weird. Okay, so the system I planned on using isn't accessible. Time to punt, not a big deal. Hey, let's try this one and see what's here. All right, so this is an internet-based system running in the cloud. Oh, it's just going to be one of those days, isn't it? Oh, no, wait. I could actually typed it in right. Wow, netstat-r. Who knew Chris would have that much trouble typing in that simple command? Awesome. All right, so what are we looking at here? We're looking at a routing table for this particular system. Routes are handled most specific to least specific. So the place you kind of want to look to kind of figure out how it's going to handle is you actually want to start with this GenMask section here, right? The more masking bits that are in play, the more specific the route. That's what the system is going to look at first to make its routing decisions. So for example, this mask is the most specific mask on this system. So that's what's always going to get verified first to see if that route's applicable to wherever the traffic is going. So example, if my traffic's going to 1.2.3.4, well, that doesn't start with this addressing, so it would skip to the next one after that. But if it does start with 161.35, well, yeah, now it's going to go off and send it this way instead. Notice my default route entry has no masking bits. So this is the least specific entry that's here. So this is why it kind of becomes default. So anything else I go in and I say I want to, route this way and route that way and all the sorts of other fun stuff like that. How do they take precedence over the default route? Well, it's because their mask is more specific. Now, that does open up the possibility to be able to do some weirdness, and I'll kind of talk about that in just a little bit. Now, netstat-r is kind of the old-fashioned way of going in and looking at the routing table. The new way to do it with Linux is IP, is it route show route? I think it's route show. Yes. Now notice we've got basically the same information here, right? Here's my default route entry. Now, it's a little bit different here. Here it's saying go through the gateway. Well, it doesn't tell us what the IP address is. We'd have to go look up and see what the gateway device is. Here we're actually getting the IP address of the gateway, so that makes that a little bit easier. It's also telling us what interface it's going out of. It's also telling us, is this something that's been statically assigned? Or you might see it say dynamic, which means it's learned it through some sort of routing table function. So, but again, pretty much the same information. One of the things you can do, and I don't have it running on this system, so let me go back to the slides again for a second. Yeah, this entry here. So notice, so this is kind of similar to what we're just looking at, right? We get a default route entry, we get a couple of specific routes here, but I got this entry here called black hole. What's that? You can actually do some pretty efficient firewalling via your routing tables. For example, let's say, so 218.92, what's that? That's the ChinaNet backbone. There is a lot of malicious traffic that originates off of the ChinaNet backbone. They're constantly scanning for SSH, they're constantly trying to break into websites. Unless you specifically do business in China, there's probably not a whole lot of reason to bother talking to that network because most of the traffic is going to be malicious in nature. So I could go up and I could set up a firewall rule for that, right? And the firewall is going to use up a certain amount of cycles to go through and, strip the packet apart and do comparisons to figure out that, yeah, okay, this is actually something that should get dropped. But a quick, dirty way to fix this problem, even without a firewall, is just to go in and create a route entry that says, hey, anything going to 218.92 is a slash 16, so that's with a mask at 255.255.0.0, so that's that whole ChinaNet backbone. Send that to devnull. And that's what's referred to as a black hole address. So what your routing table is basically telling the router is, hey, anything trying to go to that network, send it off into the ether. And now you don't have to worry about firewall rules. You can't route any traffic back to that network anymore. That fixes your problem. So this is kind of like a poor man's firewall method, if you will. You can go in and you can do firewalling at an IP level, be it network or single addresses, just by simply creating black hole entries in your routing table, and it'll use less CPU time in order to be able to control that traffic. Anything odd about this entry here? Okay, let's take a look at what we've got. We've got a default route entry. It's saying 192.168.69.1 is my default route. So anything should go out through there. The system learned about that default route entry via DHCP information that came from this host here. And then we've got an entry for the 4 network and the 8 network pointing to .10. Well, wait a minute. .1 is my default route. So that's my router to get out there. Looks like I've got some Docker stuff set up here. That's these entries here. I've got some specific entries down here. This is saying, hey, anything going to 192.168.69.anything, that's off of this Ethernet interface. So that's going to be a local delivery to that system there. And then here's my route entry to get out. Here's an individual system. But I've got so my default route entry up here, that looks like it's primarily responsible for getting traffic off of that network. What are these route entries? Those route entries are saying, hey, if you're trying to go to 4 dot anything or 8 dot anything, Send it to the system at 69.10. What's going on there? Someone has convinced my routing table, probably through ICMP redirects, that they are a more specific route to get to those particular networks. So if you want to talk to 4 dot anything or 8 dot anything, oh wait, that's a good chunk of Google's networks. So any Google type traffic you might be wanting to do, send it to that system as well. I'm saying a couple of things. Hey, is it a monitoring tool? Is it a proxy? Could be either one of those. It could be something evil. The point is this system is now going to start sending 4 dot anything, 8 dot anything traffic to this .10 address. What errors are going to pop up in the screen? None. What errors are going to get logged to, the var log directory in any of the syslog files? None. This doesn't get logged. This doesn't get recorded at all. This is one of the scariest things about when we talk about like the importance of IP communication and being able to rely on it. One of the things we tend not to talk about is that when these routing tables change, you don't, as an end user, necessarily see any errors that might tell you something bad is occurring. So if you were the user of this system and all of a sudden some of your traffic is getting routed to some other machine, you're not going to be privy to that unless it doesn't work for some reason, like, maybe IP forwarding is turned off on that host, in which case it'll break connections. You'd notice that. But if IP forwarding is turned on and someone's going in and sniffing or maybe making changes, yeah, you're not going to get any errors. This is considered normal for all this to happen in the background without you knowing what's going on. So part of my 111 root table output. Oh, cool. Thank you for sharing that. Why is that not logged? Good question, Linux girl. Um, MAC address changes, route changes are considered maintenance, and they tend not to be logged by most operating systems. Now, could you force this to get logged? Yeah, maybe, but it'd probably take some coding on your part. I'm not aware of anything that goes through and does that logging by default. If folks are familiar with something that will, now, I'm not talking about on a router, right? If I have a routing device and that routing table changes, there are definitely ways to set up logging on that. But if I'm on an endpoint system, if I'm using a Windows desktop or a Linux desktop or a Mac for that matter, and my routing table gets changed, I haven't seen anything that by default is going to go through and log that for you. So yeah, so the Windows stuff. So let's take a look at that. So with Windows, oh, come on, be a little smaller, please. That's just way too big. That's a little more readable. So with Windows, the first thing it always does is it prints out, hey, here are all the network interfaces on that system. Yes, I have a lot of them. Here's the interface and number. That's always nice because I can reference things based on its number instead of having to type out, this long weird name anytime I want to talk to a specific or address a specific interface with what I'm doing. So I'm always going to get interface information first, and then after that, I'm going to start seeing my routing table information. Notice this line here, metric. What's that? Metric is how many hops does it cost to go that way? And metric is different depending upon the routing protocol being used. For example, anybody who's used RIP, the routing internet protocol, or the RIP, routing internet protocol. Anybody who's used RIP before probably looks at this and says 331 for a metric? What? No, you can't go higher than 15. Yeah, with RIP, you can't have a route entry that is higher than 15 hops. RIP won't support networks that are more than 15 hops away. But this is more for like setting priorities, right? Like the higher the number, the least preferred the route is. You can actually get away with using bigger numbers when it's set statically. Yep, and then at the bottom, this goes through and just kind of tells me a little bit about what's going on with my interfaces in IPv6. So again, kind of similar information. Come on. There we go. Gee, Windows Terminal doesn't want to go away. What a surprise. So yeah, we kind of talked through this. So there are basically, so is the metric the number of hops? So good, so great question, Jelly Beanster. It depends upon what routing protocol I'm using. If I'm doing static routing, really it's just a preference. But if I'm using RIP or OSPF or something like that, it is going to express a number of hops. So I kind of need to know what routing protocol did it come from, and it will tell me that whether it was learned static or dynamic. If it's static, yeah, that means it's manually programmed, and then it's just a preference. So I've got four ways that I can go through and kind of maintain routing in my routing table and what it looks like. And the first one is the one that most people are used to, static. Right? Static is usually just, hey, there's only one router to get off my network. I'm going to create a static route entry that says anywhere you want to go that isn't the local network, send it to this one router. And for most environments, especially small to medium size, this works out perfectly fine. Then we have dynamic routing protocols, and they kind of fall into two categories. The first category is it tries to draw a picture of what the entire network looks like. The second category doesn't worry about how to get to specific IP addresses per se. It's more about reachability. What do I need? Where do I need to go to kind of get to that? Because there's probably only one possible path, maybe two, to deal with anyway. And I'll get into those as we kind of go through. But that middle category, the I want to paint a picture of what all the routes look like, there's two different types of routing protocols that are used. There's distance vector, and then there's link state. Distance vector is the oldest of the two. Distance vector works off of secondhand of information. So imagine I'm a router, right? And then there's another router named Bob. And I'm a router with two interfaces, and I have the 10 network off of one side of me. So I advertise to Bob, hey, Bob, I can get to the 10 network in one hop. Well, Bob looks at that information and says, great. In that case, I can get to the 10 network in two hops because I got to go through Chris to get there. And it will advertise that information back to me. Well, I'll look at that and I'll say, oh, Bob is saying he can get there in two hops. And I'll say, oh, hey, Bob, that's awesome. I have a more preferred route to get there. I'm connected to that network, but it's good to know I can use you as a backup to get to that network. Well, wait a minute. No, I can't, right? If I lose connectivity to that 10 network, Bob's getting there through me. So that entry he's advertising saying he can get there in two hops doesn't really apply to me, right? That doesn't really work that way. So one of the problems you can run into with distance vector is basically incorrect route entries, right? It looks like Bob can get there in two hops, and Bob can so long as I'm online. But if I assume Bob can get there in two hops where I can usually get there in one, if I lose my connection, I'm going to look at Bob's entry and I'm going to say, oh, Bob can get there in two hops, so now I can get there in three. Well, then Bob will look at me and say, oh, well, Chris can get there in three, so now I can get there in four. And then I'll look at Bob and say, oh, hey, Bob can get there in four. Well, now I can get there in five. And you see what's happening here, right? We run into this count to infinity problem, although it's not really a count to infinity, it's a count to 15. Because with RIP, I can't go any higher than that. Ping pong flapping. Yep, absolutely. Absolutely. So one of the benefits of distance vector is that it's pretty memory efficient. It's pretty fast to set itself up, but it takes longer to recover when a problem occurs. And some route entries cannot be quite as accurate as you might think they are. But it tends to be used on smaller networks. If I've only got like five or six networks, RIP is fine. A distance vector routing protocol is perfectly fine to go through and use. Link state is the other dynamic routing option where I'm going to try and learn where every single network is specifically. And what link state does is with link state, everybody draws their own map. So what I'll do is I'll say, hi, I'm Chris, and I connect directly to the 10.1.1.1 network, the 10.1.1 network, the 10.1.2 network, and the 10.1.3 network. And then I'll blast that out to everybody. All other link state routers, will grab that advertisement and propagate it out across the network to all the other routers as well. So a router that's sitting like, let's say 5 hops away from me is sitting there saying, oh, hey, Chris directly connects to these 3 networks. Sally directly connects to these 2 networks over there. Raman connects to these 4 networks over there. And it's almost like a jigsaw puzzle, right? Think of it as like a jigsaw puzzle. It'll sit there and try and jigsaw the puzzles together to figure out who's directly connected to what networks and what are all the possible paths to get to anywhere. The downside, it takes more RAM and CPU to build a link state routing table. The upside, it recovers very quickly. If the network figures out, hey, Chris is offline, well, now I look at the map, Bob or whoever can look at the map of the network it drew and just pull me out of it. And now that hole is gone. And now whatever's left, that's what the network looks like going forward from here. Bang, we very quickly recovered. We don't have the, count to infinity problem that I was talking about before. So if I've got larger networks, I'm probably better off using some form of link state protocol instead. Path vector routing is when the network is so damn big, we can't keep track of every single logical network, in which case all we kind of work with is reachability. And let me talk about that one first, and then I'll step back. BGP is a great example of that. Think about how many networks there are on the internet today. And there's literally hundreds of thousands, if not millions, maybe more. Now, imagine how much RAM it would take in a router to record those hundreds of thousands of route entries. I mean, it would make routers expensive as hell, right? So it doesn't make a whole lot of sense to try to keep track of every single network, especially since there are usually a limited number of paths from point A to point B. There are what's referred to as peer points between, internet service providers, and those get negotiated, and who might need to pay to peer with who gets negotiated as part of it. But the concept is, if you're on, let's say, the Comcast network, Comcast has agreements with, I think it's 3 or 4 different other ISPs to maintain peer points. So that means your traffic needs to go out one of those, 3, 4, 5, whatever the magic number is, points to get off of the Comcast network. Those are the only options available. Well, with that in mind, does it really matter how, if I'm on the 1.1 network, does it really matter how many hops away this is? Do I need to know that to try and get traffic there when there's only one possible path that can be followed to get there? Well, no. At that point, hop count doesn't really matter that much, right? What kind of matters is reachability. I need to know, oh, hey, to get there, I need to go through ASN1, which will then go through the backbone and peer to AS3. AS3 is the one that'll directly connect to that 2 network. So from here to here, I'm worried about reachability. After here, now I might worry about specific routes and how many hops and all of that other fun stuff after there. So BGP is what's referred to as a path vector routing protocol. We don't need to keep track of hop count every single entity. All we need to worry about is what's the general path to be able to go in and get there. Now, we said static tends to be the way most of us do routing today, and it works perfectly fine. System starts up, it goes talks to the DHCP server, it gets an IP address, and it's told where its default route entry is, and everything's happy after that. But when you need to get into dynamic routing protocols that could learn and recover when routes go down, RIP was our distance vector example that we used. OSPF, honestly, is my personal favorite. That tends to be used in larger networks. But if you're talking on the internet, BGP is your only option. Now, remember I said one of the problems we have is that when these route entries change, we're not necessarily getting updated about that. In other words, if I'm talking to a website out on the internet and it's 15 hops away from me, if that suddenly changes to be 24 hops instead, it's not like I get a little dialog box that pops up in my web browser that says, oh, hey, it's now an 8 additional hops to get here to this website. Do you want to continue? No, we're not going to see anything like that. So there's not a lot of logging at the endpoints to kind of identify when this stuff takes place. Now, there is logging on the routers, and logging is great, but logging doesn't prevent attacks. It just tells us how bad this successful attack was, right? And that's one of the things we kind of run into with BGP. Initially, we kind of, there were not that many peer points. The internet was relatively small in the 90s, so it was pretty easy to go in and say, hey, this router can only advertise these certain routes to me. This other router can only advertise these other specific routes to me, and that's it. And it was fairly straightforward to keep track of that manually. Well, as the internet started growing in loops and bounds, all of a sudden it becomes a lot harder to be able to keep track of that stuff. Kapgar was saying, is that based on a layer 3 advertisement? Absolutely it is. Yep, it's based on the advertisement of the IP addresses that are reachable for that particular autonomous system. So once that happened, it was kind of like the fire hose got opened up. In other words, if you can't know for sure who should be able to advertise what routes, well, now you kind of have to trust them coming from anywhere because BGP doesn't have any validation process built into it, right? Like when you talk to a website, there's this whole digital certificate system, and we'll get more into that a little bit. And yeah, okay, there's some scary stuff when you get to the bottom of the rabbit hole, but there's at least some infrastructure in place so that you can validate that the website you're talking to is actually the site that you're supposed to be talking to, and that this information it's sending you is from that legitimate web server itself. There's some validation you can go through and do. With BGP, we don't have a whole lot of that, especially since things started growing so quickly. So one of the problems we start running in today is what's referred to as BGP hijacking. So with BGP hijacking, it works pretty similar to what we were looking at earlier on that static table, where if I go in and I advertise a more preferred route to get someplace than the legitimate router, traffic may start coming to me instead. Now let's see. I had a couple questions. Does Comcast still do weird tunneling on the back end? Possibly. I know they were doing an awful lot of throttling for a while there. They would, if you were, I ran into this with like Netflix, right? I'd be like streaming a video, and all of a sudden, Netflix would reset the connection and kill it. But when you looked at the packets, the TTL that was coming in as part of the streaming data, that would have a TTL of like 50. And then all of a sudden the reset that supposedly came from that system would have a TTL of like 253. Well, no. There's no way Netflix is only 2 ops away from me. There's no way that came from Netflix. So Comcast definitely does some shady crap on their back end. But are they still tunneling stuff? That I'm honestly not sure of. Let's see. Capgar was saying, does this issue go back to a group of hackers that met with Congress, got milk, etc.? Um, it's worse than that. There's actually been companies that have set up business models around doing this types of stuff. Some have gotten in trouble for it, some not so much. Um, yeah, and I'll get into the specifics of like an example in just a little bit. Let's see. There will be a man in the middle to hijack and make the config changes. Correct. Well, so not necessarily. If I control a BGP router, or if I can get access to a BGP router, I can enable these types of changes. And this gets kind of funky, right? So like one of the things I miss of the early internet days is that how do I want to say this? Um, we weren't as worried about pissing people off and shutting stuff down. Like back in like the 90s, if you spammed a lot of people, All of a sudden, gee, your network disappeared from the BGP routing tables on the internet. You couldn't talk to anybody anymore, and no one would have any idea how that happened. But gee, all of a sudden, your spam doesn't work anymore. And until you could prove spamming would never, ever, ever be an issue from your network, for some reason, those BGP routing tables kept getting corrupted, and you couldn't communicate at all until you fixed your damn shit. And then is uh, who could manage this, got more oversight, that type of possibilities started going away. So now you get into things like, hey, so if a BGP router in, let's say, China or Belarus starts advertising incorrect routes, what do you do? It's a legitimate BGP router, people appearing with it. What do you do? Well, first of all, you might not notice at first when it takes place. Second, hey, it's a legitimate ISP, so you can't just completely shun them anymore. This stuff is a little bit harder to deal with than it actually used to be back in the early days. Back when the internet was more of the Wild West, it was actually a tamer, safer place than it is now. We like to say the early 90s was the Wild West of the internet. I would honestly say it's more Wild West now than it was back then, just because we were able to do a better control at kind of keeping things in line. Could you do a man-in-the-middle attack? Yeah, I'll talk about that more in just a second. Probably it's Comcast. Yeah, I agree. All traffic to China. Hey, it's happened. How would you even notice? Yeah, that is a problem. And yeah, let's kind of actually talk about that. So here's a good example. So Renesys, so they were this company up in New Hampshire. They basically used to get a download of all the BGP routing tables and kind of monitor what was going on the internet. And one of the things that they detected back in August of 2013 was that traffic that should be able to go from Mexico to Washington directly, all of a sudden, because someone was messing with the BGP routing tables on the internet, a more preferred route was being advertised through Belarus. So now uh, credit card transactions, traffic that was going to diplomatic agencies, instead of going directly to Washington, was going through Belarus, where then it looked like it was getting routed through Moscow, and then was making it to Washington after that. That took place 38 times that they were able to detect. And again, because your endpoint doesn't log any changes, because like all of a sudden, instead of Washington, D.C. being 14, 15 hops away, now all of a sudden it's 25 hops away, you don't get an error message around that. It just happens. And everything just seems to keep working. So you don't notice any difference. So BGP attacks, these are bad. And these are kind of nasty. Now, do VPNs take care of this? Yeah, they can. If your data is encrypted and authenticated, so long as there hasn't been a problem with initial authentication. I'll talk about encryption and authentication and VLANs and all of that in a later class. But the Achilles heel in the whole thing is initial authentication. To this day, we still don't have solid initial authentication. We have, digital certificates, which we've decided is good enough, but it's not bulletproof by any stretch of the imagination. So will VPNs fix stuff like this? Well, it could fix people from sniffing it. It could fix people from changing it. Absolutely. So long as they didn't compromise initial authentication as well. If initial authentication got compromised, everything else immediately falls apart right after that. Based on physical distances, latency would have increased as well. Yeah, not to mention Belarus isn't known for having high-speed internet. So, yeah, would there have been more latency? Absolutely. But come on, let's all be honest. When was the last time you noticed the internet was slow that you immediately said, "Oh crap, did somebody hijack BGP? Quick, let me drop to the command line. Let me trace route the IP address I'm trying to go to and see if the hops that it's going through make sense." I mean, we tend to kind of just say, "Oh yeah, it's running a little slow. It'll get better." and, not worry about it unless it's a really huge problem. So black holing networks. I mentioned this one a little bit earlier. Um, but this is a valid method of doing traffic control. And in fact, before we had firewalls, this was our primary method for doing that. If you wanted to be able to block a geographical area or a specific organization or what have you, this is the way to go about doing it. And it was just a simple matter of going in and creating a route entry for it. So for example, I did so let's say I'm seeing attacks coming in from this IP address and a number of adjacent IP addresses to this as well. Well, when I go in and I run this whois command, this tells me that that network, right, this IP address is part of this network. So it's a, /16. It's a class B size. It's a pretty big size network. And that's part of the ChinaNet backbone, right? And let's say I'm looking at my logs and I'm seeing a lot of 218.92. Something addresses attacking me. Um, if you don't run fail to ban on your systems that have SSH exposed to the internet, please set it up this weekend. Please get it up and running. Please start going through your logs. One of the interesting things to me is ChinaNet, on the ChinaNet backbone, there are clusters of systems that have been coordinated to work together. So what you run into, if you're not familiar with fail to ban, you can set it up so that, or it sets itself up by default, so that if somebody tries to log into your server via SSH, if they fail 5 times, they get shunned for, I forget if it's 15 minutes or an hour by default. It's some period of time. So for the next 15 minutes to an hour, they can't try to brute force passwords anymore because they can't even connect to the system. But after that time expires, now they can go in and start hitting it again. And what I've noticed by running fail to ban is that you'll see an IP address from ChinaNet come in. It will try, like, let's say admin is a login name, and it'll try a bunch of passwords, and that system will get locked out. Well, another IP address that's part of the ChinaNet network will immediately jump in and pick up where the last one left off and keep trying until it gets locked out. And then another IP jumps in and starts trying that again. So this isn't like some script kiddie in the basement trying to do some password guessing. This is well-financed, coordinated attacks that are coming out of that network. So if you don't have a legitimate reason to go through and, talk to that network, it may not be such a bad idea to go in and kind of get rid of it. So again, I, went in and just did a whois lookup to see what's the prefix for the network. Well, now I know it's a /16, so 218.92 dot anything. And yeah, hey, look, this system is reachable. And then what I did is I went into one of my routing devices and I said, okay, I want to add an IP route. I want to name it black hole, and it is for traffic going anywhere. And notice I didn't give it a gateway. I didn't say send it here. When you don't give it a gateway, at least with Linux, it says, oh, you must want to send it to dev null. Dev null means send it nowhere, right? Just make it disappear. Ooh, it's vapor. Boom, it's gone. I didn't even know it was around in the first place. So now when I say IP show route, here's my default route entry here, but here's my black hole entry that says, yeah, anything going to 218.92, don't let it get there. So now what'll happen is any traffic coming in from that network would still make it to my network. But any replies that try to go back are going to get sent to dev null. So unless it's an attack that they can do with one packet, the first packet in a session, it isn't going to be successful anymore. In other words, if they're trying to do SSH brute forcing, that isn't going to work because you need to complete the TCP 3-packet handshake before you can try and brute force that SSH password. Well, you can't finish the TCP 3-packet handshake if I refuse to send back SYNACK anymore, because if my system tries to send back a SYNACK, my router is just going to send it off to dev null instead. All right, I saw a bunch of different questions come in. Black hole equals drop. Yes, black hole means very efficiently drop using less CPU time than you would get out of like a stateful inspection firewall. Let's see, we got a bunch of other ones in here. Somebody shared a link to fill the band. Thank you for that. Long live Pi-hole. Oh, I love Pi-hole. Pi-hole is like one of my favorite tools on my home network. I love Pi-hole. There are some applications that, I I hate taking money out of people's pockets, but there's some apps that like if you don't shut off the banner ads popping up, the app just becomes completely useless. And Pilehole is awesome for fixing stuff like that. John was saying, I always assume it's DNS. Yeah, it could be DNS, it could be routing. You know, it could be either or. Let's see. Someone shared failed to ban. That's awesome. I just missed that. What did Chris just say that we need to do this weekend? What I said you need to do this weekend was, now I forget. So I guess it couldn't have been that important. I think it was run, fail to ban. Yes, it was run, fail to ban. So fail, FAIL, the number two, BAN, ban. Somebody shared a link to it. If you're on a Linux system, you can do an apt, install fail to ban, and that'll install it on your system as well. Awesome, awesome tool for kind of locking down your system. I'll do a class just on fail to ban as part of the series if folks are interested in that, because you can do a really cool stuff with that. Let's see. I prefer blocking port 22 to the port. VIP tables, good idea. Fail to ban set on other open ports, also a good idea. Is there a way to look up all the China networks with that whois command? Um, there is, I forget the syntax for it. You can go in and do a search on um, the additional information field here, the AS name. There is a way to go through. Well, hey, grep, right? So one of the things I could do is I could go to Nick near net and pull down all of the all the autonomous system numbers, and then just grep for ChinaNet, and that will pop them all up for me that way too. So that's another way around it. Black hole equals drop. We talked about that. Shh. Okay, cool. Block China. Yeah, I mean, it's not so much block China. I mean, certainly there are other areas in the world that are hostile. It's more about limiting your exposure, right? Like, it's kind of like, so when I park my car at night, I try not to do it in the worst place in town so people don't steal my side view mirrors. Now, why park my car in an area where I know side view mirrors will get stolen if I don't need to, if I don't have any, if I don't live there, if I don't have friends there, if there isn't a business there I want to go to, why would I ever choose to park my car there and put my car at risk? This to me is kind of the same thing. If there's areas of the internet that you're not doing business with and they're responsible for a large number of attacks, why let them talk to you at all? Why even bother going there? Let's see what else we got. Can you get a list of ISPs per country and then block them? You could. Yeah, you could. There's lists online of all the autonomous system numbers and who they've been assigned to. You can go through those lists. One of the things we're doing with the new AC Hunter that maybe what I'll do is I'll make sure that we have this resource publicly available. Is we go through and we summarize a bunch of different lists that looks at who's attacking who. And then we go through and we look at what autonomous system numbers they are part of. And then what we're doing in the new version of the tool is we're looking at which networks are we seeing no attacks originate from at all, and which ones are in like the top 10. And that becomes a minor modifier to the score of a system. So the concept is, hey, if my host is talking to a network that no attacks are associated with right now, I'm going to feel a little better about it. I still want to run it down and figure out what's going on, but I'm not going to freak out. It'll probably end up being okay. But if my system is talking to a network that is one of the 10 worst networks on the internet right now, yeah, I definitely want to run that down. That may very well turn out to be something bad. And it probably wouldn't be too hard to kind of open source that list to people in case they wanted to go through and grab it. So if there's interest around that, go ahead, throw it into Discord, and I'll talk to Bill. Tell you what, Bill's not here to defend us himself. So anyone who feels like we should assign that task to Bill to make that list publicly accessible so anybody can use it, just go ahead and throw that into Discord. And if enough people agree and Bill doesn't say, no, I won't do it in Discord before the end of this webcast, then we'll go through and we'll assign that task to Bill. How's that sound to everybody? Can you get a list? Yeah, we just talked about that. ISP, usually subnets go geo though. Well, so the list we're using is broken out by autonomous system number, but you can usually figure out so there's an additional database that you can sync to that MaxMinds has a database that says, hey, this autonomous system number is usually propagated out in this geographical area. You know, these subnets within that autonomous system number are in these geo areas. So you could do that if you want to. We can't make that publicly accessible because MaxMind has some licensing around the stuff that they do. But you could probably do it yourself if you really wanted to. Let's see. ISPs buy blocks off the, yep, they do. Although most get pretty well identified at this point. Yes, please, 100%. Yeah, okay, so it looks like we're all in agreement. We all need to give Bill extra work to do since he's not here to defend himself. That's awesome. And Radis is posting a list to the geolocation information. That's awesome. Cool. So yeah, black hole on the route. We talked about that. Dead route walking. So yeah, like I said, so traffic, yeah, a firewall will stop traffic from that network from coming in. Doing it through routing, a single packet can still make it in, but replies are never going to make it back. Now, does that mean we can throw away all our firewalls? Well, of course not. Because with a firewall, I can do things like, hey, TCP 80 to that server is okay, but don't let anybody talk to any other ports. You can't do that at a routing level. But from a, I can do sections of network that I want to go through and drop traffic to because I consider it a potential hostile entity. This becomes a real easy way to go in and automate it, because really, what do you need? You need to run a script over SSH to get this to work. I mean, that's pretty straightforward. So it's pretty easy to go through and automate this whole thing. So that's routing. Now, VLANs. I know it might seem kind of weird to some people that we're talking about VLANs this week instead of last week, but one, we already had full class last week, so I kind of ran out of time. But the other is we tend to look at VLANs as being layer 3 segments, right? Like a VLAN is supposed to be its own little logical segment, and it is. It's a way to create virtual networks on top of a physical medium. So I might have, one Ethernet network, but I might put multiple logical networks on top of that that are identified by different VLAN numbers. There's a couple of ways VLANs tend to get used. The most common by ports per port on a switch. So I might program the switch to say, hey, you're part of VLAN 5. So any traffic associated with VLAN 5, that's going to go out that particular port. Or I can do it by modifying the tags that are inside the frames of information that are traveling on the network. That's another common method as well. Most environments may use a combination of the two. So the port one's pretty straightforward, right? That's just an admin function on the switch itself. How does it work when we go in and we do this inside of a frame? Well, the way it works inside of a frame is, you may remember this from last week, right? So here's our Ethernet frame. And we said the first thing that's going to be there is the MAC address. The destination MAC address. The second piece of information stored in that Ethernet header is going to be the source MAC address. And then the third thing that's going to be recorded is the type. And we said if it's a type of 800, we know that it's going to an IPv. This is going to have an IPv4 packet inside of it, but it could be IPX. It could be a bunch of other different types. So one of the nice things about Ethernet is that it is separate from IP. You can use Ethernet to carry other protocols by IP simply by changing the type field here. Well, that's what we did with VLAN tagging. So when the type is 86DD, that identifies this as being a VLAN frame. So immediately we know there's going to be a frame inside of a frame, if you will. In other words, there'll be a VLAN frame that's going to have some information about where this packet can go and its priorities and stuff like that. But it's also going to have a type field, and that type field is now going to serve the purpose that this one used to, which is that this is the protocol field that you're going to find after this one. In other words, this is going to be if it's type 800, that's going to be an IP packet. Chris, how do you block China when China is coming from Azure, AWS, Cloudflare? Oh, that's easy. Just block all of AWS as well. No, I'm kidding. You're right. If it's a um, if it's coming from another network besides the one you blocked, that isn't going to work. And that's totally, you know, totally understood. And it's definitely not a cure-all. By blocking ChinaNet, that doesn't mean, oh, hey, life is good now. I can get rid of all my endpoint software and there'll be, happy ducks swimming around in my data center. And yeah, no, no, it's a way to solve one problem that's relatively efficient. Hey, this network, I know I'll never talk to it. Therefore, anything trying to go to it, just drop it. And now I don't have that overhead on my firewall. AWS, hey, I need to get a little bit more granular with that. I'll let TCP/80 from certain things. If I see some type of hostility, I might want to react to that accordingly. Yeah, but you're right. If it's located someplace else, we can't go there. Wow. Oh, I am impressed at just how quickly you found a duck meme to toss in when I use duck. That is awesome. So yeah, basically we've gone in and we've just created a new header and we've inserted that in the way, and that header has our VLAN tagging information associated with it. And it's this 802.q stuff here. So we've gone from so again, the Ethernet frame would normally have a type of 800. Now it's going to have a type of 8100, but we know it's still an IP packet because we're going to maintain the identification here. Now, weaknesses with VLANs. So first off, any issues with this are all local. By that I mean, if I'm 15 hops away from you, there's not much I can do to screw around with your VLANs. It isn't going to happen. Remember what we talked about last week when we talked about layer 2? Remember what we said happened at every router? All that frame information gets torn off and thrown away, right? The only thing that continues onward is the packet information. So if I create something to try and mess with your VLAN and then try and send it across to the internet to you 15 hops away, guess what happens when it gets to the first router? All that VLAN stuff is gone unless it's programmed to do otherwise. So you get the idea. So this tends to be local-based attacks instead. But since this is information getting tagged inside of the frame, and most of our security technologies like HTTPS, IPsec are based on layer 3 and above, these don't do anything to protect any changes that take place here. In other words, if I go in and I say, oh, hey, I'm going to change the ID from 10 to 15, and that'll allow me to see these packets and sniff them, well, nothing in IPsec, nothing in TLS is going to prevent that from taking place. Nothing is going to allow you to detect that that took place because this VLAN tagging, like the Ethernet header, is down at layer 2. And layer 2 changes are completely ignored by our VPN protocols. So while VPN protocols may help encrypt the data and provide some level of data privacy, it can't stop it from being sniffed in the first place. It can't stop layer 2 attacks from taking place. They're not designed to protect against that type of thing, nor could they be. It's not like this is an oversight. It's not like somebody said, hey, let's create, TLS and, nothing bad ever happens at layer 2, so we don't have to worry about that. No, wait, now we know that bad things can happen at layer 2, so we'll incorporate it in. No, you can't, because that layer 2 gets changed constantly. Like we said, every time we go through a router. So we'd never be able to validate packets. It's non-functional. So yeah, and why am I beating a dead horse here? I'm beating a dead horse here because I've talked about layer 2 attacks before, and I've seen people say, oh, well, hey, TLS will take care of that. TLS fixes that. And that's only a partially true statement. It's true in that the data is now encrypted, so you can't sniff it in clear text anymore. It does protect that portion of it, but it doesn't stop those layer attacks from being successful, getting your traffic routed someplace else. Someone could still capture those packets. Someone could sit on them. One of the challenges, and I'll get into this on the day I talk about encryption, but one of the challenges we run into with encryption is we tend to be short-sighted. We tend to look at how long would it take to break, like we use an AES 256 a lot today. And we're saying, oh, hey, it's secure because, it would take, a billion years to crack it or whatever the magic number ends up having to be. So we don't need to worry about that. Well, you know what? That was true of DES in the 70s, right? Back when Robert Morris Sr. wrote the DES encryption protocol, it was, oh, this will take, millions of years to crack with common, with current computer processing power. And, we would need at least, 75 buildings that hold one computer in each to be able to have any chance of trying to crack this in that 1,000-year period of time. But processors got faster, they got smaller. So by the time we got into, the early 2000s, it was like DES encryption. Yeah, I can crack that in an hour, no problem. Right? Well, AES is kind of the same thing. It's hard with the processes we have today, but it may not be so hard with the processes we'll have 5, 8 years from now. If I can capture your data and your data will still have value 8 years from now, yeah, I can go through and I can do something like that. DES 7-character key. I think it was 8, but it's been a while since I've played around with DES. Multi-layer switching. So the last thing we'll kind of hit on for today. So what is multi-layer switching? So it's not really multi-layer switching. What it really is it's more optimized routing is probably a better way to look at it. So with routers, we tend to implement them in software. So most routers aren't that different from like your computer, right? They run a processor, they have RAM, you load an operating system, which is software, you run that operating system, it has different features to it. I mean, for all intents and purposes, there isn't that much difference between, let's say, a Cisco router and a Linux system, right? It's just the Cisco router is dedicated for LAN type function or for routing type functions. When you talk about a layer 3 switch or a multi-layer switch, really what you're talking about is we want to optimize that routing process as much as possible. So rather than having software as an operating system, we're going to do it in hardware because we can make these things accessible faster. The upside, it runs faster, right? It can make faster routing decisions. The downside, your operating system is programmed into chips. It is really hard to go through and make changes. It's not like, Linux or Cisco where you can just patch it. Hey, here's a new image, load this new image, bang, we're off to the races from here. No, you've got to go through and you've got to reburn the hardware to fix that. Well, that means that any security vulnerabilities that appear become really hard to go through and try and rectify after that. So these tend to be more useful for internal routing because they focus more on speed than functionality. But just keep in mind that even though they're internal, so they're less likely to get attacked than, let's say, your border router, that doesn't completely take attacks off the table. And it's entirely possible that, if someone can, let's say, get a beachhead on a Windows system, they may not find your, hardware-based multi-layer switch and attack that and, be able to fly under the radar for a long time because it's really hard to try and install any types of patches on those things. So next week, we are going to be taking a break. I'm going to be in Vegas at RITA Boom. I'm going to be racing some cars. I'm going to be going to Cirque du Soleil and, having a couple of nice dinners. So I am going to be offline for most of next week. So a week from now, let's see, that would be the 23rd, we are not going to be doing a class. But the following Friday, we will come back and I'm going to talk about IP addressing and subnetting and how that works. I'm going to talk about table conversions and how we convert between binary and maybe decimal or ASCII when we do packet decodes and why things might look a certain way. And I'm also going to talk a bit about data obfuscation as well. So that'll be 2 weeks from today. But I do want to thank folks for spending your Valentine's Day with us. Shelby went in and shared a link along with a code you can use to get get one of our mugs for free. So please feel free to go ahead and take care of that, take advantage of that. And with that said, I think that's about all I got. Keith, did I miss anything?
No, not at all. In fact, you were all over the questions as well as everyone else in Discord. Uh, yeah. Again, this was great, Chris. Thank you for doing this. Again, another solid subject and information. And again, a huge thanks to all the people on Discord, not only engaging, but answering questions. And
Yeah, we have an awesome community, man.
we really do. And and I definitely want to pass out a kudos because, even though that we may not be actively answering a lot of the questions and others that have joined Discord are answering questions, we do monitor for incorrect answers, right? So we want to
Yep.
make sure that nobody like propagates any incorrect information. And not a single person needed any correction today. So thank you for all the great correct answers.
Well, I don't know. My wife might disagree on that. I need correction on occasion. So,
I'm sure we all do.
but maybe I just got away with an hour of not needing that. So, and HK made a comment about, hey, have fun, don't drive too fast. We need you back. But, everybody sees my motto at the end of this. Hey, everybody, drive fast and take chances. So it would be wrong of me to not take my own advice. So
Yes. Awesome.
I like Eric's comment. Enjoy Vegas. Remember, no one ever lost money there. They always know right where they left it. So one of my jobs in late high school years and early college years was working at a horse raceway track. I saw enough during those couple of years to know I will never ever gamble. Because technically, there's no such thing. It's not gambling. It is set up for someone to specifically win, and that's usually not me. So awesome. All right. Thank you, everybody. Thank you, Keith, for jumping in. And hey, we came up with a lot of work for Bill to do, so I think Bill's going to know better than to skip one of these again. And I'll catch everybody on the flip side. Everybody take care. Have fun.